Hi, Giovanna. Okay, you ready? Okay, excellent. So good afternoon, everyone, and or good morning, depending on your time zone. So welcome to the non-European non-associative, the European non-associative algebra seminar. It is my great pleasure to introduce Giovanna Carnovale from the University of Padua, who will talk to us about Nichols algebras over simple groups. So go ahead, Giovanna.
Thank you very much for the invitation. I have to apologize because a part of the talk would be very close to Leandro's talk of about a month ago, but I need to repeat a lot of information just to give a context and to be self-contained. So I put this in brackets, the non-associative, because in fact Nichols algebra are associative algebras, as we will see, but they share a lot of properties, and a lot of the techniques that are being used are very similar to Lie algebraic, Lie theoretic techniques. So in fact they are pretty close to Lie theoretic objects. So first of all, what is a Nichols algebra? So I want first to start with giving some examples of algebras that everybody is familiar with, or at least many people are. The first one is something that everybody has seen, and that is the symmetric algebras. So we have the symmetric algebra, and we also have the exterior algebra of any vector space. And for the people that are pretty much into Lie theory, you can also prove with the theorem of Marc-Rousseau that the positive part of the universal enveloping algebra of a semi-simple Lie algebra is a Nichols algebra. So from these examples, you can already see that these three algebras that belong to the same family share very different features, because the symmetric algebra is infinite dimensional, but it's quadratic. That means their relations, are generated in degree 2. The exterior algebra is finite dimensional, but is still quadratic. And UQ of n is infinite dimensional or finite dimensional according to whether Q is a root of unity or not. And it's again a graded algebra, but the relations are controlled up to a degree that depends on the Cartan metrics of this algebra. So even if they belong to the same family, they can have very different behavior. So let me now show how you construct a Nichols algebra. So let me start from the example of the symmetric algebra, and then we will build on this example. So what do? The symmetric algebra is constructed as a quotient of the tensor algebra. So this is by the ideal generated by all the possible exchange of two vectors. And this can also be seen as the tensor algebra quotient by the kernel of 1 plus tau, where tau is the usual flip of two tensorons in a vector space, in a tensor product of vector spaces. Okay, but then in this case we know that the relations of the symmetric algebra are completely generated by what happens in degree 2, but we could also indeed add all the possible permutations in any n-fold tensor product of V. So we could also view this as the tensor algebra quotient by the kernel of the direct sum for n bigger than 2 of the action of, you can take any permutation of Sn and consider the sum along all the permutations on the same number of elements, and this acts on the n-fold tensor product of V, and I want this to be, I want to quotient TV by the kernel of any of those. So I could also write it as TV modulo the direct sum of these kernels. So from this we see that S of V is a graded algebra. It's the quotient of a tensor algebra by a graded ideal. And we want to construct the Nichols algebra in a similar fashion. What we are going to do is to replace the action of the symmetric group by a braid group action. So, and in order to do that, we need some ingredients. So as for all these algebras, we had to start with a vector space and a law that tells us how to interchange tensorands. So now we generalize this. So we consider a braided vector space. So this is the datum of a vector space and an operator on V tensor V that satisfies the Yang-Baxter equation or braid equation. That is the following. You want that when you act by C on, so I want to act on the three-fold tensor product of V, and I want this to be, this equation to be satisfied. Okay, so when I have a pair like that, a V, a vector space, and such an operator that is called a braiding, then I have enough data to construct a Nichols algebra. So I want to mimic this construction. So I will take the tensor algebra over V, but I have to tell what will be the ideal by which I'm factoring. So to do that, I need to sort of lift the symmetric group to the braid group. So let me recall to fixed notation what the braid groups are. So for n bigger than 2, I define the braid groups Bn for each n is the group with generator sigma I for I from 1 up to n minus 1, such that sigma I, sigma j is equal to sigma j, sigma I if I and j are far apart. And otherwise, sigma I plus 1, sigma I must be equal to sigma I plus 1, sigma I plus 1. So you can immediately see that Bn maps surjectively over to the symmetric group by mapping sigma I to Si, which is the transposition of I and I plus 1. And this action, say this group homomorphism has a section that is set theoretic. It's called the Matsumoto section. And how do you do that? Well, this law is telling us that if you have a permutation that you write as a product of this kind of adjacent transpositions and is of minimal length, so it will be some I1, I1 plus 1, IL, IL plus 1, then I map this element, which is an element in the symmetric group, to sigma I1, sigma IL. This works as long as I do this for elements of minimal length. So words of minimal length. And it's a theorem that this thing is well defined. So if you choose two different words of minimal length, then the element in the associated element in the braid group will be the same. Okay, so now I have a way to go from the symmetric group to the braid group. Let us go back at what we had here. So we had a sum along the symmetric group, and I want to go up to the braid group. And here I had an action of sigma, so of any permutation on the n-fold tensor product of V. Now I want to have again an action of elements in the braid group on the n-fold tensor product of V. And to do that, I use my datum that I still haven't used, so the braiding. So given a braided vector space VC, I have automatically a representation of the braid group for any n on the n-fold tensor product of V. So there is a representation rho n of the nth braid group. Oops. Given as follows. So the element, the generator sigma I, is mapped to the operator that acts trivially on almost all components except from the ith and the ith plus 1. So this goes to the identity V tensor I minus 1, tensor C, tensor the identity of V on n minus I minus 1. Okay, so now I define the Nichols algebra of the pair V comma C as the following. So this is BV and is the quotient of the tensor algebra. It will be a graded algebra, so I want to kill a graded ideal. So I want the following. So I want the kernel of, this will be a graded linear map, is the sum along all possible permutations, just as for the symmetric algebra. But then I take first the Matsumoto section. So this element here is an element in the braid group. So I can apply the representation. This is a representation on the n-fold tensor product of V. So it's so the kernel is a subspace of an n-fold tensor product of V, and I take the quotient of the tensor algebra by this vector space. And this vector space is in fact an ideal, of the tensor algebra. In fact, you can show that this is really the thing I quotiented out for is the kernel of an algebra map from TV to to some algebra that is called the shuffle algebra. But okay, so what we know now is that we have the Nichols algebra. It's a graded algebra, but according to how V is, it can have completely different behaviors. So when we take the symmetric algebra is obtained from taking C equal to the flip operator. The exterior algebra is obtained by taking minus the flip operator, and the universal enveloping algebra of a positive part of a Lie algebra is obtained by taking an operator of the form, you take V1 up to Vn, a basis of the vector of a vector space, and you take this will be your simple roots, and you take C of Vi tensor Vj is equal to Q to the Aij Vj tensor Vi, where Vi is the Cartan matrix. This is for symmetrizable, and otherwise you have to symmetrize. Okay, but you have many other possibilities for a braiding. So up to here, the braidings, if you see, are very simple. Essentially, they are always the flip operator composed with some diagonal map, sometimes very easy, sometimes more complicated. But in fact, the family of braidings is much richer than that. And so I want to give you some further braidings that are of interest for this talk. In fact, they will be the braidings we have been working on. So so now we give some braidings coming from groups. So we take a group G and we associate to it, let me say it's finite. And for this talk, from now on, I will take the field of the base field to be C. The complex number is not really necessary for many of the things I'm telling, but it's for the purpose of this talk. I think this is the right setup. So I take a finite group and I want to construct a braided vector space. And to do that, I take something that is called a Jeter-Driffield module. So I take V, a G module, that is also G graded. That means V is the direct sum of some homogeneous components labeled by the elements of G, and with some compatibility that is given by the fact that when I act by the elements H in G on the homogeneous component corresponding to G, then I get V, H, G, H inverse. So these objects were studied by several people. I think that the first time they appeared in the work of George Lustig. He was studying representations of finite groups of Lie type, and he was viewing them as sheaves on the finite set G. And this condition would give like some G equivariance of these sheaves, and he used them for classifying unipotent characters. This appeared in the Arcata conference proceedings. But then after that, many people studied them, and several people proved and reproved the classification of the simple objects in there. We will come to that. First, I want to make you observe that when G is abelian, this condition is just telling us that this decomposition of V is a decomposition into G stable subspaces. But when G is non-abelian, then this is really something new. But that is telling us that if that conjugacy classes will play a role in this type of modules. So these are called Jeter-Drinfeld modules. And maybe to give some context, so the name of Jeter comes because he introduced this family of objects in the general framework of Hopf algebras, and they also carry the name of Drinfeld because it was later observed by several different authors that this condition is telling us that this V is a module for the so-called Drinfeld double of the group G. Okay, so but I promised you braidings from these objects, so let us give the braiding you can associate to any such gadget. So I want to construct a map from V tensor V to V, and this is done as follows. So I have a grading and I have an action of G on V. So I want to say what is the braiding doing on a pure tensor where the first component is homogeneous, and then it will be extended linearly. So what you do is you interchange W and V as with the usual flip, but then you act by the degree of the element V on the element W. And it's an exercise to check that if I start with a Jeter-Drinfeld module, then this C will be a braiding. So if I talk about a Jeter-Drinfeld module from now on, the braiding I will be considering will be this one. Okay, so we have defined Nichols algebras, and we are interested in Nichols algebras that are associated to braided vector spaces that are constructed from a group with this procedure. And the main questions we are interested in, and in fact, the main question I will be interested in this talk is for which Jeter-Drinfeld modules V is the Nichols algebra finite dimensional. So one can attack this question by different methods, and essentially one of the typical things you do is you first consider different types of groups and see what happens. Before we do that, I first want to mention why this is interesting. So. Other people could tell you that they are interesting for other reasons, but these are my motivations. And one is, the first is the classification of finite dimensional pointed Hopf algebras. This is a program initiated and carried out by Andruskiewicz and Schneider, with a lot of results by several different authors that I will mention. So the work, as I mentioned, was this approach using Nichols algebra was introduced by Andruskiewicz and Schneider. They wanted to study finite dimensional pointed Hopf algebras. So these are Hopf algebras that belong to a very important family, because universal enveloping algebras and quantum groups are pointed, group algebras are pointed, and say many of the interesting examples of Hopf algebras are pointed. And if you want to classify them, with the only method we know, passes through the classification of finite dimensional Nichols algebras over groups. So the Nichols algebras I've been introducing. But there are other occurrences of Nichols algebras of groups that have been of interest. One is the application of Nichols algebras to the proof of Malle's conjecture. It was a conjecture about distribution of fields extension due to Malle. So it's in number theory. And this was done by Ellenberg and Westerland. And in fact, you can realize many of algebras also as whole algebras, and they have relations with intersection cohomology on sim. So and there are many other applications. Okay, so let me tell a bit what is known about this question. So when G is abelian, then the classification is done, and it relies on work of Heckenberger. And then Anchiono described generators and relations for these finite dimensional Nichols algebras, and then this was applied to the classification of finite dimensional Hopf algebras. And then, okay, and I should add that some cases were done by collaborators of these authors. And then another case that has been pretty worked out is when the Jeter-Trimfeld module, or in general the braided vector space, decomposes. So also the case in which V decomposes as let's say W1 plus WR, where V is a braided vector space, and also these are braided vector spaces. With compatible braidings. And here, let me mention, I promised that this had to do with Lie algebras, and in fact, both these result, but also this result were obtained by making use of diagrams like Dynkin diagrams, and so a generalization of Dynkin diagrams and the techniques pretty much were pretty much inspired by Lie theory, and this is work of Heckenberger and Vendramin. And then this was also presented by Leandro Vendramin a month ago in this seminar. Then we also have like great achievements that have been obtained for G solvable. So this was, there is work that follows from work of Heckenberger, Meir, and Vendramin that was generalized by Andruskiewicz. Heckenberger and Vendramin. Okay, what is less known is what happens when G is simple, or when G is really far from being solvable, and when the module here doesn't decompose. So let me first mention the fact that how does a simple Jeter-Drinfeld module look like? So we go back first to the definition that I gave before. So you can see from here that if I take a conjugacy class in G, this condition here, the compatibility condition, is telling me that if I take VO, the Jeter-Drinfeld module, the subspace of the Jeter-Drinfeld module that is supported only on O. So I take this is the sum of the elements only along the elements of O. Then this is certainly G stable, and it's again G graded. So it's again a Jeter-Drinfeld module. So if I'm looking for simple Jeter-Drinfeld modules, so Jeter-Drinfeld modules that have no sub-Jeter-Drinfeld module, then certainly the grading must be supported only on one single conjugacy class. And if one homogeneous component is non-zero, then certainly all the homogeneous component in the conjugacy class will be also non-zero. So this tells us that conjugacy classes are really relevant when you want to study Jeter-Drinfeld modules. And in fact, the simple ones are made this way. So I take an element G in my group. I take the stabilizer of G. This is a subgroup of G. And then I take an irreducible representation of this centralizer, this stabilizer, and I induce. So this gives me a G module. But then, by, say, the definition of induction, in this case, this is just CG tensor CH W as a vector space. And so I can view identity tensor W as a subspace of V, and I declare that the graded component associated to G, the element I started with, is this subspace. And then there is a unique way to extend the grading to V to have a Jeter-Drinfeld module. And all simple Jeter-Drinfeld modules are made this way. So the data I need are a conjugacy class or a representative of a conjugacy class and an irreducible representation of its centralizer. Okay, so there is a fact that makes simple yet dreamful module really relevant, and is the fact that the construction of Nichols algebra is functorial. So it means that if we have an inclusion of braided vector spaces or of yet dreamful modules, say braided vector spaces, then the corresponding Nichols algebras will also have an inclusion. And so, say, if we are able to control the finite dimensionality of simple yet dreamful modules, or at least if we know that some simple yet dreamful modules carry an infinite dimensional Nichols algebra, then this will be brought to any other yet dreamful module containing them. So we can reduce to this fact. Okay, so the thing is that when you want to study, so we want to study simple groups. So how do Nichols algebras over simple groups look like? So that means Nichols algebras associated to yet dreamful modules over a simple group. And the point is that nobody has seen one except from group algebras. So if there is one, it must be really very good hidden, and the conjecture is that they are all infinite dimensional. I need to add a small comment on this, infinite dimensional. If G is simple, non-abelian. We have examples when G is abelian, but when G is simple and non-abelian, we have seen no finite dimensional example. So let me correct to something that I just missaid before. I said we have never met one, Nichols algebras. What I was thinking in the back of my mind is I was thinking about Hopf algebras and finite dimensional Hopf algebras. So let me correct what I said. How do Nichols algebras over simple groups look like? Well, if the group is non-abelian, then they're all infinite dimensional, probably. Up to now, we never met a finite dimensional one. And the reason why I misspoke is that this conjecture would imply the following fact for finite dimensional Hopf algebras. So this would imply that the only finite dimensional complex pointed Hopf algebras H such that the group of group-like
of H is a finite non-abelian simple group, are the group algebras.
Okay, so this conjecture would really have a deep impact on the classification of finite dimensional pointed Hopf algebras. And what is the status of the conjecture? So I'm going to steal a very nice picture that I was shown by Meinolf Geck, and it's pretty cute. And it has an author, which is Ivan Andrus. So it has copyrights. You can find it in the internet, but it's the table of finite simple groups. And I want to show you what is the state of the art of this conjecture up to now. So we don't need to care about the cyclic groups because we are interested in finite simple groups that are non-abelian. And this is the table that is listing all finite simple groups. So for people who haven't met this before, you have the alternating groups that are over here. You have sporadic groups over here. And you have the large family of finite groups of Lie type that are over here. So again, we have the word Lie, and Lie theory, you can see is hiding here behind with the Dinkin diagrams. So all this, say that the large part of this family of groups consists of, say, you can view them as algebraic groups, simple algebraic groups over finite fields, or groups of fixed points of a simple group defined over the algebraic closure of a finite field, fixed point by an automorphism, ensuring that the group you get is finite. If you do this procedure, you don't get usually a simple group. You get something that, say, roughly speaking, up to quotienting by the center gives you a finite group. Okay, but let's say they are very close to taking algebraic groups over finite fields. So let me tell what is the status of the conjecture. So this part, the alternating groups, for this part, the conjecture was proved by Andruskiewicz, Fantino, apologize for not writing all the names, Grania and Vendramin. And also the sporadic groups were almost all handled by Andruskiewicz, Fantino, Grania and Vendramin, and then something by Fantino, Vendramin, and also Beltran Cubillos. And the three groups that are left doesn't mean that we know nothing about these three groups. We know that there will be a few conjugacy classes that might support a Jeter-Drinfeld module that might have a finite dimensional Nichols algebras. But for many conjugacy classes, this is so for those groups for which we don't know things, we know we have a limitation on the type of conjugacy classes that could be supports of Jeter-Drinfeld modules. Okay, so let me go here. Then here there are the Suzuki and Reed groups, and for these the conjecture was proved by myself and Mauro Costantini. And then many of the groups that you see left were handled in a series of papers by Andruskiewicz, García, and myself. Unfortunately, in most of the cases, we were not able to say, well, I can erase this group, because we could kill, we would work by conjugacy class type and not by group type. So what we know, so by work of myself, Andruskiewicz, and García, is that apart from the group PSL27, which you see over here, then if the dimension of Nichols algebra is finite dimensional and the Jeter-Drifel module is supported by one of these groups, then V is supported by a conjugacy class of an element where the order of G is coprime to Q, where Q is the size of the field. So I can say coprime to P, where P is, as I told you, these groups have to be seen as algebraic groups over finite fields, and P is the characteristic of this finite field. In other words, you want semi-simple elements. So the only possible Nichols algebras over finite simple groups that are finite dimensional, up to the work with Nicolas and Gaston, were essentially support of Jeter-Drifel modules supported by semi-simple conjugacy classes. But we could exclude already some of them. So we could exclude certain groups when the characteristic was odd, and for people acquainted with Lie theory, when the longest element is equal to -1. So this one was already killed. So the conjecture was proved for this group. No, not for this one. Okay, and now there is work I've been doing with Nicholas Andruskiewicz that is using on the one hand results of Getty sites on what kind of finite simple groups can contain certain semi-simple elements and certain tori, and also at the same time we are using some of the work that I mentioned by Andruskiewicz, Eckenberger, and Vendramin, and on solvable groups, and we could attack further classes. So what we know is that the symplectic groups are all handled, and we know that the odd orthogonal groups are handled, and in fact we are and what we also did was developing a method by using Seitz approach to subgroups of finite groups of Lie type containing a semi-simple element in order to build a strategy to ensure that that the conjecture holds. So so let me just mention what is the main idea that is behind most of this work, not only the one we are doing now, but also the work that we have been doing in the past, and that also the other colleagues I mentioned have been doing in the past. And the idea is the following. So the key idea. So we know that it's enough to look at simple Jeter-Drinfeld modules, but the simple, so enough to look and we know that they are parameterized by pairs that are a conjugacy class and an irreducible representation of the centralizer. And what we want to do is to provide conditions on the conjugacy class, ensuring that we don't have to care about the centralizer. So if the conjugacy class in the group has a certain structure, then you will know that no matter what W you will place close to it, the Nichols algebra will be infinite dimensional. And let me give an idea of what kind of structure you would need. Well, the idea is that you have your, so suppose you have a subgroup of G, let's say L, a subgroup of G, you have V, a Jeter-Drinfeld module over G. And you have a subgroup such that when you intersect the class, the conjugacy class of some element, it splits in more than one class. So you want to split it, say, as L space, L space. So you have an action on L on this intersection, and this splits as into more than one conjugacy class. Then, and assume that you want that these two conjugacy classes do not commute completely. Then say you can consider the following situation. Then you can consider the restriction of your Jeter-Drinfeld module to the part that is supported by L. So this is just the sum of the elements along all the elements of L, of the graded components associated to here. And then if your Jeter-Drinfeld module was simple, then the support was just a single conjugacy class. Let me say this one. And if it splits, then it means that this module is no longer simple. It's a Jeter-Drinfeld module for a smaller group, but it's no longer simple. And so you can invoke the results by Heckenberger and Vendramin. In fact, this condition is a technical condition that allows us to use Heckenberger and Vendramin's condition, but you need to add further assumption. And these further assumptions come from the fact that the result of Eckenberger and Vendramin on modules that are not simple is telling us that there is a really small list of Jeter-Drifel modules for which that are not simple, for which we have a finite dimensional Nichols algebra. And so the extra conditions ensure that we are not in this small list. Okay, so if you see now, we have transformed a problem that was and group theoretic and representation theoretic into a completely group theoretic problem. I consider conjugacy classes, and I'm looking for subgroups for which the class splits and do not commute, and some further reasonably mild conditions. So it's a completely group theoretic problems into the structure of the simple groups you're interested in. One last thing that I want to mention is that these conditions are of interest also because they propagate. We know that every finite group has a quotient to a simple group, and these conditions propagate in the sense that they propagate to lifts and to overgroups of our group. So if we get information about the simple groups, in fact, at the same time, you get informations about overgroups and covers. Okay, so this is what I wanted to report on. So let me leave the periodic table.
Okay, thank you very much. Thank you very much, Giovanna. It was a very nice talk. Are there any questions or comments? Let me check the chat box. Oh, there is a question. Okay. Mm-hmm.
Yeah, so thank you for the talk. I don't know if you can see me, but yeah.
Yes.
So what is the state with the other groups that you didn't cancel? You have some classes that you still don't know, or you couldn't even try. How is this? Like for example, this E63, X6, E6Q, or the others. This the one that are kind of pink.
Okay. So the status is that we know that, I'm sorry. In fact, so let me say, we also did G2. G2 is done. So the status is that we have a theorem that translates the requirement of type C into Lie theoretic terms. So you need to find a subdiagram of the Dynkin diagram such that certain things happen. And the status is that now we are checking this Lie theoretic condition on the remaining groups. So it takes some time, but let's say we pretty much simplified the problem. It won't work for all conjugacy classes, but essentially you do this as is typical with finite groups of Lie type. There is most of the cases can be handled by general arguments, and then there will be a few with small q's or I don't know when u is very small or where some power is a prime, for which you have to do ad hoc considerations.
Thank you.
So
very nice.
I think what will be a problem will be more this PSL2 will be the hardest in the end.
PSL2, but with like bigger than 2 or all n or what?
No. PSLN, we know, I didn't write it, but in fact, PSLN here is done. So PSLN, it doesn't mean that all classes are of type C, but that at least for the classes that do not satisfy this criteria, then they can be handled by abelian methods or by other methods. So that they don't propagate, but at least we know that there is no Nichols algebra. So no, the problem is PSL2 because it has very few subgroups. Even when you want to do restrictions, it has very, say, even if you want to use subregs of size, small prime size, it's you don't find many. You don't find affine regs easily.
Which classes, do you remember which classes are still like open in PSL2?
The semi-simple that are not split, so it would be elements that are of order dividing 1 plus q.
Okay.
Not all
Thank
of them,
you.
but these are the hardest ones. Yes.
Okay. Here are there other comments or questions? Well, if not, then let's thank Giovanna again. And we hope to see you all next week for another seminar.
Yes. Thank you very much.
So thank you, Giovanna.
Okay.